Okay, so in this presentation, I'm going to argue that Emmy Noether's work on symmetry and conservation laws represents a genuine paradigm shift in physics. And rather than introducing a new physical law, she completely changed how physicists understand what a law actually is. So she showed that conservation laws are not fundamental assumptions, but consequences of deeper symmetries in nature. And to explain why this counts as a paradigm shift, I'll be using Thomas Kuhn's model of scientific revolutions. So moving from normal science through anomalies and conceptual tension towards a new framework. Now, I'm going to start by looking at how conservation laws were understood before Noether, and why that understanding even eventually became unstable. So, before Emmy Noether, conservation laws were already central to physics, but they were understood as these separate fundamental facts about the world, which here are kind of represented as separate jigsaw pieces that were unlinked. So physicists knew that quantities like energy, momentum, and angular momentum were conserved, and these principles worked extremely well in practice, but each of them stood on its own. So they were each justified by experience and by direct calculation, rather than by a deeper theoretical reason. And there was no unifying explanation for why these different conservation laws existed, or why they appeared across so many different areas of physics. They were treated as these independent principles and just not parts of a single underlying structure. Now, in Kuhn's terms, this period represents a stable phase of normal science. So these laws were trusted, they were useful, they were rarely questioned, and yeah, this is even though their conceptual foundations were just not fully understood. So now moving on to this conservation through formalism, during what Kuhn would call a period of normal science, the physics became increasingly successful through this use of the powerful mathematical formalisms. But they started with Newton and later was refined by Lagrange. So the physicists, they developed these systematic methods for describing motion using equations of motions, and they were extremely effective. So once the equations were written down, certain quantities could be shown to remain constant over time. For example, these are the three kind of conservation laws I'm going to keep referring to. Momentum, angular momentum, and energy are the three kind of separate jigsaw pieces I'm using as a metaphor throughout this presentation. But yeah, if I expand on these examples, in collision problems, the equations simply implied conservation of momentum. In systems with rotational motion, the same formal tools led to conservation of angular momentum. And in many mechanical systems, energy can be shown to remain constant as it changes between kinetic and potential energy. So what's important here is that each of these conservation laws were derived case by case. So they followed from the mathematical formalism, but there was no single principle explaining why these different quantities were conserved or why they appeared universally across physics. And as a result, the normal science during this period was highly successful, but it was conceptually limited. And physicists knew how to obtain the conservation laws and how to use them effectively, but the deeper reason behind their existence remained unexplained. So, now I'm going to kind of expand on these emerging anomalies in classical physics. As classical physics developed, these conservation laws continued to work remarkably well. That's kind of one of the most remarkable things about Noether's theorem, is that these laws they worked. So there was no real reason to kind of dig deeper. But it's important to note that even though they worked, there was a number of conceptual anomalies that still began to emerge. And they weren't failures of prediction, but they were kind of these failures of explanation. It was the backbone and the understanding of these conservation laws that was lacking. And one growing issue was that they lacked a common foundation. So energy, momentum, and angular momentum kept appearing across these different theories, but there's no single principle explaining why these quantities and not others were conserved. And at the same time, physics became increasingly dependent on these abstract mathematical formalisms. So, for example, here I have three big examples. In electromagnetism, energy was no longer associated with just particles, but with fields spread throughout space. So, this is kind of one of the concepts which we explore now in S7 physics, which is potential, electric potential energy, and it raises completely new questions about where energy is and how it moves. So secondly, these tensions were even made even clearer with the development of special relativity. So quantities like energy and momentum turned out to depend on the observer's frame of reference, and time itself is a part now of the dynamics. And so these conservation laws still held, but their physical interpretation was much less it still is much less intuitive. And similarly in general relativity, the problem was kind of even further deepened, because space-time itself becomes a dynamic, and even defining a globally conserved energy now becomes very difficult, and even in some cases actually impossible. So yeah, in Kuhn's terms, these are classical anomalies. They exist in paradigm remain successful, but its conceptual foundations are increasingly strained. And the mathematics works, but the meaning behind the results becomes unclear. So this suggests that there is this deeper organizing principle that is missing. So now we're going to move on to this crisis, this need for a deeper principle. So by the early 20th century, physicists found themselves in what Kuhn would call this conceptual crisis. And these conservation laws again appear to be universal. Energy, momentum, and angular momentum, they showed up again and again and again across mechanics, electromagnetism, and relativity. But these existing theories offered no common explanation for why these particular quantities were conserved. And the situation was not that physics had completely stopped working. In fact, it was actually more successful than ever at the time, but the foundations of that success has become very unclear. And the conservation laws were reliable, powerful, and even indispensable, you could say, but they seem to rest on, this no deeper principle. That's kind of the core, that is the core crisis of this paradigm. And this raised a simple but unsettling question, which is, why are these quantities conserved at all, and why these laws and not others? These are the questions I've repeated throughout these slides. In Kuhn's terms, this marks the point where normal science begins to strain under its own success, and the search begins for a new organizing principle that can explain rather than merely reproduce these regularities. So before introducing Noether's theorem itself, I'm going to try to be kind of somewhat clear about what physicists mean by symmetry. So in physics, a symmetry means that the laws of nature don't change under a certain transformation. So what Noether showed is that each of these symmetries corresponds to one of the conservation laws we saw earlier as separate puzzle pieces. So the first example is time translation symmetry. So if the laws of physics are the same today as they are tomorrow, then the outcome of an experiment does not depend on when it is performed. And this invariance, or symmetry, in time leads directly to the conservation of energy. So here, the pendulum illustrates that energy may change form, but its total remains the same over time. Again, potential and kinetic energy. So the second example here is spatial translational symmetry. So if the laws of physics are the same everywhere in space, then a system behaves the same regardless of its location. So this symmetry leads to conservation of momentum, as illustrated here by the rocket continuing its motion when no external forces act on it. And the third example is rotational symmetry. So if the laws of physics don't depend on orientation, then rotating a system does not change its behavior. And this invariance under rotation leads to conservation of angular momentum, which explains why orbiting bodies speed up and slow down in a precise, predictable way. Now this links straight to Kepler's law. I'm pretty sure it's Kepler's second law, which actually just states this exact fact. But what's interesting is, obviously, when Kepler developed this theory, he didn't actually know that it was because of this symmetry. It's Noether that proved this. So yeah, at this point, the puzzle pieces we saw earlier, they're kind of starting to fit together. Energy, momentum, and angular momentum, they're no longer independent facts, but they each kind of correspond to a specific symmetry of nature. And what appeared kind of fragmented, well, it fully did, it appeared fragmented before, it's now part of a single underlying structure. And this is what Noether proved. So the crisis we just saw is resolved by a fundamental shift in perspective, which was introduced by Emmy Noether. This was the breakthrough. Instead of asking which quantities are conserved, she asked a different question, which is what stays the same when a system is transformed. And this is the key conceptual move of the new paradigm. The focus shifts from physical quantities to invariances or symmetries. conservation here is no longer assumed as a basic principle, but it's derived from symmetry. So at the top right here, maybe this will help you further understand symmetry. We know what lines of symmetry are. Lines of symmetries are. So the butterfly image illustrates this basic idea. Here the object remains unchanged under reflection, but in physics, Noether's insight was that similar invariances, not only in space but also in time or orientation, have deep consequences for how the systems behave. Now, more precisely, she proved that every continuous symmetry of a physical system corresponds to a conserved quantity. So here we explored three conservation laws, kind of three symmetries and conservation theories, but she actually developed an equation that proves this for all kinds of symmetry. So we explored time translation symmetry leading to a conservation of energy, spatial translation symmetry leading to a conservation of momentum, and rotational symmetry leading to a conservation of angular momentum. And these is what previously appeared as these three separate laws, but they now follow from a single organizing principle. Now the diagram at the bottom left represents the action principle. So it shows that when a small transformations leave the action unchanged, the equations of motion imply a conserved current. Now this is where the abstract mathematics enters, but the crucial point is conceptual. The conservation laws emerge from invariance. Finally, the formal statement of Noether's theorem is at the bottom right here. This is the algebra with the derivatives here. And it shows how general this result is. So it just tracks back to what I've just said. It applies across all fields: mechanics, field theory, and later quantum physics. And with this shift, conservation laws are now no longer mysterious facts about nature, but they're absolute necessities and necessary consequences of symmetry. So now, what is this new normal science? What is physics after Noether? So after her work, physics has entered this new phase of normal science under a fundamentally different conceptual framework. This new paradigm that's established has symmetry become the starting point of theory building. So instead of postulating conservation laws and then checking whether they hold, physicists begin by identifying symmetries of a system, knowing that conservation laws will follow automatically. And these physical laws are now defined by what remains unchanged under transformation. So this way of thinking quickly became central to quantum mechanics. So what's really interesting is these new physical fields that we still explore to this day, they all very quickly apply Noether's theorem, such as also classical and quantum field theory, and later also to gauge theories and particle physics. So these symmetry principles determine the form of the fundamental interactions. Very importantly as well, Noether's contribution was not only forward-looking, but it completely clarified a deep conceptual problem in Albert Einstein's general theory of relativity. So in general relativity, space-time itself is dynamic, and the traditional notions of global energy conservation has become very problematic. And Einstein was very aware of this tension, and he recognized that something conceptually subtle was going on, but the existing language of physics struggled to explain it. And yeah, thanks to Noether, she managed to show that the conservation laws in general relativity, they're not actual just fundamental facts about energy or momentum themselves, but they're actually a consequence of these space-time symmetries. And when those symmetries exist, conservation laws follow. When they do not, classical conservation laws may fail without indicating a flaw in the theory. So this completely reframed the issue, and it turned what looked like a problem into this structural feature of the theory. And Einstein, fully recognized this significance of this contribution. He later described Noether as the most significant creative mathematical genius thus far produced since the higher education of women began. And this praise just reflects more than personal admiration, but it acknowledges that Noether's work provided this conceptual clarity that modern theoretical physics absolutely required at this time in the 20th century. So this is what a stabilized paradigm looks like in Kuhn's terms. The earlier crisis has now been resolved, the older theories are reinterpreted rather than discarded, and the scientific research has now proceeded with this new shared framework. And after Noether, this physics as we know today, it absolutely does not abandon the conservation laws, but now we finally understand why they exist. So to conclude, Her work, Emmy Noether's work, qualifies as a paradigm shift in exactly the sense described by Thomas Kuhn. So first, it changed what counted as a fundamental explanation in physics, where conservation laws were no longer taken as basic facts about nature, but as consequence of deeper symmetry principles. Secondly, it reordered the conceptual structure of physics. So instead of starting from forces or conserved quantities, physicists can now begin by identifying invariances, from which laws and conservation principles follow. Thirdly, her work did not overthrow earlier theories such as classical mechanics or general relativity, but instead it allowed us to reinterpret them and fully understand them, and their whole backbone, if we could say it in that way. And this completely explains why they worked, and it also clarified their limitations. So yeah, this new framework completely stabilized into a new phase of normal science. Today, symmetry principles are central to how physical theories are constructed, taught, and also extended. And in Kuhn's terms, this is precisely what a successful scientific revolution looks like. So it's not the accumulation of the new facts, but a fundamental change in how these facts are understood. Importantly, Kuhn's cycle does not end with Noether. So even within this new symmetry-based paradigm, new anomalies have emerged. So for example, in modern physics, phenomena such as symmetry breaking, quantum anomalies, and tensions between quantum field theory and gravity showed that symmetry principles, while foundational, are not always exact or complete. And these issues do not invalidate her work or her framework, obviously, but they suggest that even the symmetry-based paradigm may eventually face its own conceptual limits, and it does. And this is exactly how scientific progress continues. So a successful paradigm stabilizes, it generates new problems, and one day these will actually give rise to another shift in how physics understands its most fundamental principles. So yeah, this was me kind of going over Noether's work and the paradigm shift she kind of marked in physics.